So thanks, Network Frontier, for organizing this wonderful wave event and inviting me to present share my research. And I'm Siddique. I'm from University of New Mexico, and I'd like to present today the symmetries in the time-average dynamics of networks. And I'd like to mention my collaborators, Francisco Sorrentino, Luis and Pecora. And today I'd like to tell about some network topologies and symmetries, and how we can partition the network, and from that and how we can build the class, how we can get the clusters, and what's the and how the clusters can show up in the time average dynamics. And for this purpose, I would discuss about on evolutionary game theory, and then I will discuss a way to reduce the graph and simulations, and finally I will show an experimental relation, which we can show the effect of symmetries. Now, what is a network? So a network is a set of nodes and edges, and nodes are connected by edges. And we define, this network can be represented by an adjacency matrix, and the elements of the adjacency matrix we define such a way that if node I and j are connected, then we put aij or and aj equals to 1. And for all of our study, we choose the undirected networks. And in the left figure, we show an example of network, and the right side we show an adjacency matrix, and the whites are the zeros and the blacks are the ones. And then we want to partition this network based on the symmetry. And now we want to know what is the symmetry. So symmetry is the permutation of nodes that leave the network structure unchanged. For example, if we swap between node 1, 2, and 3, and 4, and finally we can see that it doesn't change the network structure. And we define this, we represent this permutation as a permutation matrix, such that pi ij equals to 1 if node I swaps node j. Otherwise, it is 0. And then this is an important identity is that pi a equals to a pi. Since we are interested to partition the network, so we want to find the clusters. So, and we see that all the symmetries forms a set which forms a mathematical group, and we can find the orbit of this group from this study. And in the bottom figure, we can see that node 1 can swap 2, and 1 can swap with 3, 1 can swap with 4. That means they have the identical. They have the identical relations or identical features in the networks, and this is how we can tell that 1, 2, 3 forms an orbit. And we like to show in our simulation that these orbits comes up with similar or identical time-averaged behavior. And I like to mention some previous works did by Martin Goluboski and his team, Igor Belic and his team, and Luis M. Pecora, Francisco Sorrentino, and most of their studies focus on the symmetries. But today we like to introduce the symmetries, the role of symmetries in different types of dynamics. And we studied different types of dynamics, and today I'd like to focus on the dynamics of evolutionary game theory. So in a game, so in a network, there are two types of node. We can see in the right figure. Some of them are green, so that they are cooperators, and the red nodes are defectors. So cooperator pays a cost C, and for this cost, so someone gets this. The connected node gets the benefit B, and we form the payoff matrix. So when a cooperator is connected to the cooperator, the payoff is B minus C, and the cooperator defector is C minus C, and defector, when defector connected with the cooperator, then he just receives the benefit because defector doesn't pay anything, and defector and the connection between defector is just zero. Payoff is just zero. And then we want to see the evaluation, how the game goes on time. So for each time, so we also define the payoff and total payoff and fitness, and we define the fitness function is a function of omega. Omega is the intensity function, and for our simulation we choose low intensity functions, the evolution I like to brief about the evolution of the game. So each time step, one node is removed, and the new offspring takes place, and the new offspring decides its strategy based on from the fitness of its neighboring nodes, and we define the strategy selection function sigma, and sigma ranges from 0 to 1. And we can find the detailed description of this in the paper in the archive by Siddique and Luis Lopez and Francisco Antino. And now we like to show present the results. And on the top we see the figure of Karate Club, Bell South, and Random Peer Network. And these red nodes, they form one cluster. These blue, they are another cluster, belongs to another cluster, green another cluster, and yellow, they are from another cluster. And we see, and we plotted the frequency of being cooperator. That means how frequent a node remains in the cooperator state as the time inverse dynamics. And we can see that these red nodes, they are from a cluster, and they are showing similar time average outcome. And we see this for all the nodes. So and from this outcome, then we thought, okay, so since nodes in the same cluster, they are showing similar dynamical behavior. So why don't we think all these nodes in the cluster as one node, and if we can reduce our graph, and we can simulate the dynamics on these networks. Okay, so now I like to present how we can reduce the graph on network. So as I told earlier, that our intention is to reduce the graph such a way that all the nodes in the same cluster of the full network will reduce them as a single node in the quotient graph. And we can see the right figure is showing the quotient representation. And here we can see that all the clusters in one node in the quotient graph. And now I like to present a study by Mark Arthur et al. In one of his articles, and he showed the presence of symmetries in the real networks, and we can see that it's very often that we can find the symmetries in the real networks, and this is showing the reduction ratios. And reduction ratios, we define the reduction as number of nodes in the quotient network versus number of nodes in the original network. And the lower value of the reduction ratio tells us the higher reduction in the quotient graph. And then we wanted to simulate our simulate the dynamics of evolutionary game theory on quotient graph. And this is for this reason we adapted our simulation. And because in the full network each time step one node was removed, but here in the quotient graph, if we remove one node, that means it's equivalently we are removing the whole cluster from the full simulation. So these two phenomena is not same. So we need to have a probability of removing nodes so that we can match the full and quotient simulation. So this is why we made the selection probability such that that is directly proportional to the certainty of the corresponding orbit of the full network. And payoff and fitness equations are adapted because the links are weighted in the quotient graph. And then we presented the results. We can see here so I like to describe the results. So this squares it represents the frequency of being cooperative of nodes, and this diamonds it's showing the results or the frequency of the nodes being in the cooperative states in the quotient network. And we see a very good agreement between them. And now I like to mention about some what are the advantages we can have from this quotient graph simulation. And for this reason, I like to mention some definitions or terminologies that because we describe the advantages in terms of these terminologies. So we defined reduction ratio as the reduction ratio earlier, and now I like to define this tell about the CPU ratio, CPU time ratio, and we define the CPU time as a time as a CPU time for one iteration of the game. And the ratio, the CPU time ratio means that the ratio of one iteration in the quotient network versus the full network. And convergence time. To say about convergence time is that when we define the settling time as that when the time invariance dynamics doesn't change over time more than 5%. And this convergence time ratio is the ratio of maximum settling time of quotient network of quotient nodes and versus the full network nodes. And I like to show relative errors is a standard relative errors. And now I like to show the results. We can see that the CPU time ratio and reduction ratio has a linear relation, and that the less is the reduction ratio, the less is the CPU time, and this is how we can save a lot of we can save our computational time. And then the convergence time, we also see that it follows a linear relationship. And this is how we can. This is very obvious because in the quotient graph we compress the time, and this is very fascinating that the relative error is less than 4% for all the cases. And I like to represent an experiment. And here we construct a network with Arduino and radio transceivers. Each node is an Arduino with a radio transceiver, and we could construct a network using this wireless communication. And we continued our experiment on the evolutionary game theory on this network, and we can see that this is the result. And the nodes in the same cluster, they are showing they are producing the same time average dynamics. And so the left figure is representing the simulation in the full network, and the right showing the results in the quotient graph. And we can see the quotient simulation is following the full simulation. And the relative error we find that is around 3.5%. And we discussed the other dynamics and the role of symmetry on the other dynamics in this paper. And this is the archive link. And that's all. Thank you.